The last chapter we covered was about mostly discrete random variables and a specific discrete random variable, the binomial distribution. The normal distribution, that is the topic of chapter 4, is an example of a popular continuous distribution. That is, it's the distribution for a very popular certain type of continuous random variable. So a continuous random variable has a normal distribution if its probability density function can be written as, for negative infinity up to positive infinity, this formula right here, which isn't very friendly looking. However, that is the formula for the normal distribution curve. The notation here is going to be y, and remember this little tilde means is distributed as, the capital N means normal, and the first thing in the parentheses here is the mean of the distribution, and the second thing is going to be the standard deviation. Often you'll see the variance in the second entry there rather than the standard deviation in the normal, because knowing the standard deviation gives you the variance and vice versa. But if we differ from that, we'll indicate that to you. So in this class, you should assume that the first thing in the parentheses is the mean of the distribution, and the second thing is the standard deviation. Examples of random variables in the biological context that have a normal distribution is serum cholesterol levels, eggshell thickness, and believe me, that's widely studied for marketing purposes and such. They need to have eggshells with a certain thickness because of breaking and things like that, and nerve cell interspike times, among others. Some facts about the normal distribution that we want to know is that it's continuous over negative infinity to positive infinity. It's symmetric about its mean, mu, and it's unimodal, and since it's unimodal and symmetric, we call it a bell-shaped curve. Notice there are infinitely many combinations of mu and sigma, so we have infinitely many bell-shaped curves that are considered normal distributions. The example on the left over here is a normal distribution, right here. Notice that it's centered at 40. So remember we said it's symmetric about its mean, mu. So that means the line of symmetry is at 40. And you can see here that that looks like the case on this illustration. The standard deviation sigma for this one is 10. Now let's pay attention to the middle one. It's much wider and flatter than the first one. Its mean, mu, is 100. So the line of symmetry is at 100. And the standard deviation is 20. And the third normal curve that we're going to look at is much taller and thinner. It's centered at 120, the mean is 120, and the standard deviation is 5. So I think you can see how the mean affects the normal distribution. It just shifts it to the left or the right on the normal distribution. The mean tells you where it's centered on the real number line. Okay? So the standard deviation does something different. The standard deviation tells you how much spread there is in the values of the distribution. Notice that the standard deviation of the right-hand curve is 5. The next biggest standard deviation is the left-hand curve at 10, and the largest standard deviation is the middle curve at 20. So you can see that the curve for the standard deviation of 5 over here on the right is not very spread out if you look at what values that normal random variable would typically take. Looks like it's about between 100 and 140. For the next biggest standard deviation, sigma of 10 on the left over here, it's a little more spread out. It occupies about this much space on the real number line. And for the biggest standard deviation of 20, you can see that it occupies a lot more space than the other two. Something like that. So that's what the standard deviation does. Now, why is this curve the shortest, this one the second shortest, and this one the tallest? Well, that standard deviation is what's affecting that. What's the total area underneath any of these curves? Well, remember, this is a continuous distribution, and so the area under the curve, it's like a smoothed probability histogram, so the area should be 1 under each of these curves. Well, if you have a bigger standard deviation, so you spread these tails out in your normal distribution, imagine that being a piece of yarn. If you were forced to keep the area the same, and you stretched the edges of the piece of the yarn outwards, it would bring the top of the piece of the yarn down if you wanted to restrict that area to be 1. So a bigger standard deviation makes you have a shorter, fatter normal curve, a shorter, fatter bell, and a small standard deviation, when you pull the ends of the yarn in this way, is going to push up the top of the distribution to keep your area at 1. So a smaller standard deviation gives you a taller, skinnier bell shape. All right, so that's looking at normal distributions, shapes, and we're going to tell you sort of an agenda for this chapter. The first thing you're going to do is for a value in the distribution, you're going to be able to find probabilities associated with it. Very similar to what we did with the binomial distribution, only we're going to use a different function in R to compute the probabilities. The second thing that you're going to do is the reverse of number 1. For a probability, go backwards and find the value in the distribution. And that's going to be something called percentiles. The third thing that you're going to learn is to standardize a value from the normal distribution to find its z-score. And the fourth thing is, given a set of data, try to say whether it looks like it came from a normal distribution. So let's get started with our first order of business, and that is finding probabilities associated with the normal distribution. So given a normal random variable, we can find probabilities associated with that value from the distribution by finding the area under the curve, which is accomplished using integration, which some of you would have learned if you've had calculus course. Now we have to use numerical integration methods on this anyways. The kind of integration that you would have learned in your calculus wouldn't work here for this particular function. However, you don't need to worry about any of that because we're going to use a built-in function in R to calculate those areas for us. So again, if you have not had calculus, there are no worries here. So R is going to accomplish this using the p-norm function. Notice the similarity to when we computed binomial probabilities. We had a d binom function and a p binom function. Remember, the p binom function gave you the area including the value that you gave it and everything to the left of it. The d binom just gave you the height of the bar at an exact value. Notice we're only giving you a p-norm function for the normal distribution. We don't give you a d-norm function. When we're doing probabilities for the normal distribution, we're never going to use d-norm. We're always going to use p-norm. The reason for this is we can't compute the height of a bar for just one value in the normal distribution because that has no meaning to us. We can't assign a probability for exactly one value in the normal distribution since there are uncountably infinite number of possible values. So the thing that you need to remember is that in the normal distribution, we don't need to worry about whether we have a strict or non-strict inequality. We talked about this in Chapter 3. So we're only going to use the p-norm function. Now the p-norm function gives you the area under the curve to the left of the value that you give it. Just like the p-norm function did, it gave you less than or equal to. This is going to give you less than or equal to in the normal distribution. So you're going to put three things in the argument for the p-norm function. The value you want to go to the left of, the mean, and the standard deviation of the normal distribution. So this value right here is going to be mu, and that standard deviation that I wrote as SD, that's going to be the sigma. Okay, so first example that we have is a random variable y, which is the length of herring in millimeters. We're telling you that y is distributed as a normal distribution with a mean of 54 and a standard deviation of 4.5 millimeters. We're tasked with finding the probability that y is less than 60. So what I want you to do on every single one of these problems with the normal distribution is draw a picture. It will help keep your thoughts in order and make sure you're getting the right solution when you're computing these. So you're always just going to draw a bell-shaped curve. You can label it y, that's fine. We're going to label the mean as 54 here. And I usually just write the standard deviation up in the upper right hand corner of my picture, just so I can keep track of it somewhere. Now we want to find the probability that this random variable is less than 60. So we could draw a line for approximately where 60 might fall in this distribution, and we're going to shade in the area that we want to find. We want to find the area to the left of 60. So we need the area under the curve that's shaded in on the picture. So that area should be the probability that y is less than 60. Now how are we going to accomplish this? Well, that's going to be our p-norm function, because it gives us the area to the left of something. And we want to go to the left of 60, so that's our first thing in our parentheses. in a distribution that's centered at 54 with a standard deviation of 4.5. So let's go ahead and type this in R and see what we and we'll type in P norm. Our first value was the thing we want to go to the left of, which is 60. The mean of the distribution was 54, and the standard deviation was 4.5. And we're getting 0.909, or 0.9088. So we'll just put 0.909 here. Our next question wants us to find the percent of herring in this distribution that are between 50 and 60 millimeters long. So again, we want to go ahead and draw a picture of our distribution. And this one's centered at 54 with a standard deviation of 4.5. And I want to look between 60 and 50. So if I want to find the probability of being between 50 and 60, and then of course I can change that to a percent later, I need the area shaded in right there. So we want the probability of this normal random variable being between 50 and 60. And again, remember, it's a continuous distribution, so we really don't care about whether we write a strict or non-strict inequality, because adding that one particular value doesn't affect the probability. Only in the continuous distribution, though. You may not be cavalier like that in the binomial, a discrete distribution, because it will affect your probability oftentimes. All right, so if we want to do this, we could use P norm of 60 with a mean of 54 and a standard deviation of 4.5. And what would that give us? That would give us everything to the left of 60. So that's going to give us all this area under the curve all the way down there, right? So what can we do to only keep the area between 50 and 60? P norm of 60 gives us everything to the left of 60. We only want to keep 50 on up. So we need to go ahead and subtract out P norm of 50. So we'll go ahead and do that. Centered at 54 and a standard deviation of 4.5. Now when we did our binomial calculations, remember that we adjusted this lower one. If we wanted to keep 50 and up, then we threw away 49 and down. But remember, that was a discrete distribution where everything was whole numbers. And so it mattered, and we had to pay attention to whether we were including the 50 or not. Here, it's a continuous random variable, so it doesn't have any impact. It does have an impact if you shift it down to 49, because you've lost all the values between 49 and 50. You've lost 49.1, 49.3, 49.5. You've thrown away stuff that you didn't want to throw away. So don't adjust the endpoints on these probabilities when you're computing them. So we'll type in our statement right here, and it should give us P norm of 60 centered at 54 with a standard deviation of 4.5 minus P norm of, what was it, 50? Okay, with a mean of 54 and a standard deviation of 4.5. See if I typed everything in correctly. I think I did. And I'm getting 0.7218 or 0.722. So 0.722. Now we asked for the percent. The probability of a randomly selected herring being between 50 and 60 millimeters is 0.722. So that means that 72.2% of randomly selected fish will be between 50 and 60 millimeters long. So that gives you an idea of how to accomplish task 1 for this set of lecture notes. With a given value, find a probability associated with it. Now we're going to go on to task 2, and that is, given a probability, we want you to be able to come back out with the value that's associated with that percent. So we're going to define something called a percentile. The point of a distribution below which p% lies is called the pth percentile of the distribution. You've all heard of percentiles before when you got your standardized exam scores back. If you were in the 99th percentile, that means you did really well. That meant 99% of the distribution scored below you. So R is going to compute normal percentiles for us using a new function called the Q norm function. So instead of a P or a D, this one's a Q. When you want to find a percentile of a distribution, you want to use one of the Q functions. So Q norm takes three arguments. It takes the probability, that's the area to the left of the value you want to get out, and then the mean and the standard deviation. So let's go ahead and do an example of this. Find the 70th percentile of the herring length distribution. Again, let's draw a picture. So we've got our random variable. It's centered at 54. Its standard deviation is 4.5. And we want to find the value, we'll call it y star, such that 70% is below it. So hopefully you get the idea with the picture here of what we're trying to get out. Instead of us having this number and trying to get the area out, we have the area and we're trying to get the number out. So how do we find a percentile? Well, we use our Q norm function. So we're going to use Q norm with our probability first, and make sure you put that in a number between 0 and 1. So we'll use 0.7 for the 70th percentile. The mean of the distribution, of the normal distribution that you're trying to look in, 54 here, and the standard deviation, which is 4.5. And typing in our Q norm of 0.7, 54 is the mean, and 4.5 is the standard deviation, I'm getting 56.36 millimeters. So the value in the distribution that has 70% below it, or the 70th percentile, is 56.36. And remember, this is a value in the distribution of values. Okay? And our distribution is about herring lengths, so these percentiles get units. So a length of 56.36 millimeters corresponds to having 70% of fish being shorter than that. Now to find the 25th percent. Again, we're going to draw a picture. So I'm going to put my normal distribution here. That's not very symmetric, but hopefully you get the idea. Okay, so I draw my normal distribution and I want to find the 25th percentile. Now where do we draw where's our value going to be? Well, in the normal distribution it's symmetric. So 50% is actually below the mean and 50% is above. In symmetric distributions, then, our mean is going to be equal to our median. So that's kind of a handy fact to know. So the 25th percentile is going to lie below the mean. So we can draw it somewhere down here. And that's our y star that we'll be looking for. And we want the value that has 0.25 below it. So again, to get a percentile, we're going to use the Q norm function. We want the value that has 25% below it in the normal distribution with a mean of 54 and a standard deviation of 4.5. And so we'll go ahead and type this in. I'm just going to arrow up and change my percent to 0.25, and I'm getting 50.96. So 50.96, and again, this is a value in the distribution of herring lengths, so it gets units. So a fish with 50.96 millimeters long is in the 25th percentile for lengths. So now we want to find the 50th percentile. Let's go ahead and draw a picture. This normal distribution centered at 54. The standard deviation is 4.5. And so where is the 50th percentile going to be? We kind of already gave this away by talking about our last example. It should have 50% below the mean in the normal distribution because it's a symmetric distribution. So our 50th percentile is going to be 54 millimeters. So I could do my Q norm function if I want, but I was just trying to illustrate how you would just know that the 50th percentile is the mean in the normal distribution. So if we were going to type it in, we would type it in that way, but it's 54 millimeters. It is the mean.